Hey everybody, welcome back to chemistry. And so I want to do a final presentation where I talk a little bit more about what oxidation numbers are. And so one of the things I think you saw so far is that oxidation numbers refer to the relative deficiency or excess of electrons that an atom might have compared to its neutral self. So let me just give you some examples where the oxidation number indicates that. So for example, let's say we have here iron metal, and we want to compare its oxidation number to the iron 3+ ion. So I think what you sort of know at this point is that if you have the iron metal, we assume that this is a free element which is neutral, meaning it'll have as many electrons as protons, and so its oxidation number would be 0. Here, as we're going from the iron metal to the iron 3+ cation, it has to lose 3 electrons. And when it does, it'll have a 3+ charge. And so, therefore, because this iron ion is deficient in 3 electrons, we indicate that in the oxidation number. And so we say, okay, so this is deficient in electrons, so it's a plus. And it's deficient in 3 electrons, so it's going to be a +3. So we can take another simple example here. So let's compare the neutral sulfur atom to the sulfur anion. And so the neutral sulfur atom will have as many electrons as protons and will be neutral, and therefore free element that is neutral always has an oxidation number of 0. Now if you have the sulfide anion, what is that? Well, the sulfide anion you get when you take the neutral sulfur atom and add 2 electrons, add 2 negative charges to the atom to give you the sulfide ion. And so it has 2 extra electrons, and so we want to indicate that in the oxidation number. If it has extra electrons than normal, we put a negative here, and it has 2 more electrons than normal, so it's oxidation number of -2. So you can see that oxidation numbers clearly show you a relative excess or deficiency of electrons. But one thing you may have noticed is that sometimes we'll have a molecular compound like water. So here is good old water. Now, we've been assigning oxidation numbers to the elements in the water. And so we have told you that the oxidation number of hydrogen in the water is +1, and oxygen in the water is -2. So you might think, oh, okay, well this tells me something. That in water, what we must be dealing with is a situation where the hydrogens in here are deficient in 1 electron each, and the oxygen atom here has an excess of 2 electrons. Well, if that were the case, then the hydrogen oxygen would be ions. But here's the thing. This is a molecular compound. Maybe one of the things you remember is that molecular compounds are not made of ions. So it raises the question, how can we give oxidation numbers to these elements which are not ions, meaning that they have their full complement of electrons that they should have? These are relatively neutral atoms. How can we give these oxidation numbers to these atoms? Well, they are relatively neutral atoms, but here when we see the +1 here, what you'll see, I'm hoping in just a moment, is that the hydrogen in the water, while it hasn't completely lost 1 electron, it is only partially lost 1 electron. And therefore, we go a little further with the oxidation number and say, okay, let's make it +1. If oxygen had a -2 oxidation number, we would expect it to have 2 extra electrons. But in the water compound, it does not, but it has a partial excess of 2 electrons. So I want to sort of explain how this could be. And so let me draw some pictures here of water. Okay, so what I'm going to do is draw a picture of water as we know it. This is what I'm going to call real water. And then what I want to do is draw a picture of water as oxidation numbers see it. So we can call this fake water, if you will. So this is fake water, and then I'm going to write as oxidation numbers see it. So maybe if you looked up hydrogen and oxygen in the periodic table, you would learn that oxygen, the neutral atom, has 8 electrons, and then hydrogen, the neutral atom, has 1 electron. So let's go ahead and draw a picture of real water. And so here maybe we're going to look at the oxygen atom first. And so here is the nucleus of the oxygen atom. So oxygen has 8 electrons. It's neutral, so it also has 8 protons. And so I'm just going to put a plus here for those 8 protons. Now, where do the 8 electrons go around this oxygen? Well, you'll learn further on that the first 2 of the 8 are relatively close to the nucleus and are said to be in something called an energy level. And so I'm going to represent the energy level as a circle here. So we have 2 electrons of the 8 there, and then we have 6 more electrons in oxygen. Where are those? So let me draw those in. And so they are going to be further out from the nucleus in the so-called second energy level. And so I'm going to put 2 here like that. I'm going to put 2 here like that, and then I'm going to put 1 up here and 1 up there. And so this is sort of a simplified drawing of the oxygen atom. So I'm going to also draw this oxygen atom for fake water. It's pretty much the same thing. Here's the nucleus with 8 protons. First energy level has 2 electrons, and then the second energy level has 6 electrons like that. So now let's go ahead and draw in where the hydrogen atoms bond to the oxygen in each of these. Okay, so in real water, this is what it might look like. And so let's draw the hydrogen here on the relative right side. So here is the nucleus of hydrogen, and so its atomic number is 1. So it has 1 proton, 1 electron. So you can imagine the 1 proton in the nucleus being here. Now, where is that 1 electron for hydrogen? Well, it will be further out from the nucleus in its first energy level. So here I'm going to draw the first energy level here around hydrogen. I'm going to put its electron right there. And so you can sort of see in this simplified diagram that the 1 electron of hydrogen is going to be relatively near 1 of the second energy level electrons of oxygen. And that's good for this example right now. And so we can draw on the other hydrogen like this. And so here is the energy level, the first energy level of hydrogen. And so here is the electron for hydrogen. Okay, so now let's think about what all these electrons are doing here in the water molecule. First, let's focus in on these electrons of oxygen which are close to the nucleus. They stay pretty localized near the nucleus, and they don't really do anything special. Same thing with these 4 electrons that are not involved with bonds to hydrogens. Here, these 4 electrons stay kind of relatively localized away from the opposite side of the water molecule from the hydrogens, and so we don't really have to worry about those. Now, let's consider this pair of electrons here. One of the pair is from hydrogen, and one of the pair is from oxygen. So you might remember that water is a molecular compound, and the bonds between the atoms in a molecular compound are said to be covalent bonds, which means that these electrons are shared between the 2 atoms. So we have a pair of electrons here that's going to be shared between hydrogen and oxygen. How can we simply describe their motion in the molecule? Well, they're going to be shared between the 2 atoms, right? So imagine that these electrons here, I'm sort of pointing them out, they're going to be spending some time going around oxygen, but then they're going to be spending some time going around hydrogen. And so this pair of electrons is shared between oxygen and hydrogen. Same thing with this pair too. They're going to be shared between oxygen and hydrogen. But here's the thing, and this is kind of important, is that one of the things you're going to learn later is that due to some properties of the oxygen atom, oxygen has more of an attraction for a shared pair of electrons than hydrogen. So in fact, it is thought that this pair of electrons involved in the oxygen-hydrogen bond, they spend a lot more time around oxygen than they do hydrogen. So it's more like this. Spend a lot of time around oxygen, a little time around hydrogen. This pair, same deal. A lot of time around oxygen, a little time around hydrogen. So you can think of it this way. This oxygen now has more electron density than normal. And so to indicate that, we indicate that the oxygen end here is delta negative. the hydrogen has less electron density than normal because those hydrogen's electrons spending more time around oxygen than hydrogen, and so it has less electron density than normal. So this is going to be delta positive for this hydrogen, and this will be delta positive for that hydrogen. So when I have delta here, that indicates a partial charge, and that here we don't have a full extra charge going into an oxygen. We just have here the electrons are spending a little bit more time around oxygen and hydrogen, so this is just going to be a partial charge that oxygen has. And so that's a good picture of what is going on in the pair of electrons here in the water molecule. Now, when you're thinking about oxidation numbers, it imagines water to be looking a little bit different. So let me show you how oxidation numbers imagine the water to be looking like. So here is the oxygen atom. So let me go ahead and put in the hydrogen atoms. How does that look like in the oxidation number picture of water? So here is hydrogen's nucleus here, and then here is hydrogen's electron. And so I'm putting it with oxygen, and this makes the point that in the redox picture of water here, when we're thinking about oxidation numbers here, we imagine that the electron completely leaves hydrogen and goes to oxygen. Now, is that really going on? No. This is the real picture of water here, in that the electrons are shared between hydrogen and oxygen, even though they spend a little bit more time going around oxygen than hydrogen. Here in the oxidation number picture of water, here we imagine transfer of hydrogen's electron to oxygen. Same thing here with this hydrogen here. It's going to transfer its electron to oxygen. So again, this is really not what is going on in water. So that is why I call this fake water. But this is how the oxidation numbers see it. So you can sort of see for this reason, because there is transfer of an electron from each of these hydrogens to oxygen. Oxygens, which had 8 electrons, now in this picture has 10 electrons. It has 2 more electrons than normal. So now in this picture, you can see that oxygen atom has gained 2 electrons from the hydrogens. And so to indicate that with an oxidation number, we say oxygen has gained electrons, so we'll say it's negative. And so it has an oxidation number of -2 because it's picked up 2 extra electrons. Well, hydrogen here has, each of them has lost 1 electron, so its oxidation number is +1. So when you have an ionic compound, then the oxidation number will be the same as the charges of the ions, because the oxidation number reflects whether you have extra or a deficiency of electrons in the ions. When you have a molecular compound, it's different. Although the electrons in bonds between the different atoms of a molecular compound are shared between the 2 atoms, when we think about oxidation numbers, we pretend that's not the case. We pretend that if we have instead transfer of electrons from one atom to another. So we pretend that the compound is ionic. Now, how do we know that electrons are being transferred from hydrogen and oxygen and not from oxygen and hydrogen? Again, that is something you'll have to learn about later. But the point is, with molecular compounds, we pretend they are ionic compounds, and that is the way we can sort of assign oxidation numbers. Okay, so this is sort of important implications for understanding when do you have a redox reaction. So I want to go over that right now. Okay, so we have 2 redox reactions there on the screen, and let's talk about why they are redox reactions. Okay, so the first one is pretty easy to understand. We have iron 2+ reacting with copper 2+, and it's becoming iron 3+, and copper 2+ is becoming copper plus. Now, let's go ahead and see if this is a redox reaction. We can see it is a redox reaction is because for iron and copper, their oxidation numbers are changing as we go from reactants to products. So iron 2+ is a monatomic ion with a 2+ charge. Its oxidation number is +2. Copper 2+ is a monatomic ion with a 2+ charge. Its oxidation number is +2. Iron will have an oxidation number of +3. Copper has an oxidation number of +1. So we can clearly see that the oxidation numbers for these ions are changing as you're going from reactants to products. And also, I think you can sort of understand the reason why they're changing is because electrons are leaving one species, making it relatively deficient, and going to another species, giving that species a relative excess compared to what we had before. So you can see that here. Iron 2+ here as a reactant is deficient in 2 electrons. As a product, it's deficient in 3 electrons. That means it must be losing an electron. And so this electron will be going over to copper here, and then it will take copper, which is deficient in 2 electrons, and then change it so it's only now deficient in 1 electron. So you can see that this is a redox reaction is because what we're having here is interspecies transfer of electrons, or intermolecular transfer of electrons. We have electrons leaving one species and going to a completely different species. Okay, so let's consider the next reaction. We have here oxygen. Let me get a better pen here. We have oxygen plus hydrogen, and we're going to water. Now, I think you can imagine that this is going to be a redox reaction. It's because you can imagine here that these elements here all have oxidation numbers, and their oxidation numbers of the elements change as you go from reactants to the products. But here's the thing. We know that we're not dealing with ions here anymore. We're dealing with molecules. So these molecules don't have full charges. So how can this be a redox reaction? Well, it's because there is going to be partial transfer of electrons from one atom to another. And if you have partial transfer of electrons, that qualifies it as a redox reaction. So let me explain how that happens. So first off, let me draw our picture of water here. So here is oxygen, here its nucleus. Here are 2 electrons in the first energy level. And then here are 6 electrons in the second energy level. The electron from hydrogen, here is hydrogen here. And so here is the other hydrogen here. Here's its electron. There's its nucleus. So let me put a plus here by the nuclei here. Okay. So let's go ahead and assign oxidation numbers to the oxygen and hydrogen in water. And so even though this is not any ions in water and that this is a molecular compound, I kind of explained to you, is because here the electrons in the bond between oxygen and hydrogen are spending more time around oxygen than hydrogen. We pretend with oxidation numbers that basically they're completely transferred to oxygen. So the oxidation number for oxygen is going to be -2, and the oxidation number for the hydrogens is going to be +1. So we're going to put -2 for that oxygen and +1 for hydrogen. Okay, so now let's look at what the structure of the oxygen molecule as a reactant looks like. And so we have 2 oxygen atoms. Let me draw one in blue. And so here is the nucleus of the oxygen. And so here's a pair of electrons here. And then I'm going to draw the other 6 electrons, a pair here, a pair here, 1 electron here, and 1 electron there. Now, I guess what we'll use is, a yellow pen here for the other oxygen atom. So here's the nucleus of the other oxygen atom. Get a better yellow pen here. Okay, here we go. There's the plus here. I think I'll have to use the green pen. We're going to use a green pen now. Okay, and so here is the inner 2 electrons, and then we have the second energy level of this other oxygen. A pair here, a pair here. One of this oxygen's electrons is paired up with one from the left oxygen's. Same thing here. Another one of the right oxygen's electrons is paired up with the electrons over there. Now, As it turns out, you'll learn later with the oxygen molecule, you see these two pairs of electrons here? It's a total of 4 electrons. These two pairs of electrons are going to be shared between the two oxygen atoms. Now here's the thing, you have oxygen on the left and oxygen on the right. So do you think that these pair of electrons are going to be spending more time around one oxygen than the other? No. These two oxygen atoms have exactly the same properties. And so this pair of electrons here is going to be spending equal time going around both oxygen atoms, like this. And same thing with this pair here. This pair is going to be spending equal amounts of time going around both oxygen atoms. And so what you can see is that these pairs here, they're not transferred over to one particular oxygen atom. It's not that one particular oxygen atom is going to want them more than the other. They're equally shared. If they're equally shared, that forces the oxidation numbers for the oxygen atoms here to be 0 here. And so oxygen, molecular oxygen, has an oxidation number of 0. Same kind of deal with hydrogen here as a reactant. So here we have one hydrogen atom, and so here is its one electron, there's its nucleus. And then here is the other hydrogen atom, and there's its nucleus, and here's its one electron here. And so again, these two electrons with these two hydrogen atoms, they are going to be shared equally between the two hydrogen atoms here. And so again, because these electrons are not transferred over to one atom, nor are they spending a little bit more time around one than the other, instead they're equally shared between the two atoms. Therefore, we have to set the oxidation numbers of these hydrogens to be 0. Because again, and the reason is because the electrons are shared equally between the two atoms. We don't have a relative deficiency or excess of electrons for either of these hydrogen atoms, and therefore its oxidation numbers should be 0. Okay, so now you can clearly see that for oxygen and hydrogen, the oxidation numbers are changing as we go from reactants to products. But see the difference we have between here and what we had before? Here we have changes of oxidation number because we had electrons leaving one species and completely going to another species. And so this is interspecies or intermolecular electron transfer. Do we have electron transfer here with this second equation? Yes, we do, but it's not its case where the electrons are leaving one species and going to a completely different species. Instead, within the species, the electrons are changing the amount of time they spend around one particular atom. So here, this pair of electrons here in oxygen, in molecular oxygen, is spending equal amounts of time going around these oxygen atoms. But in water, the electrons and the bonds are no longer doing that. Instead, they're spending a lot more time going around oxygen than these hydrogen atoms. And so we do have a redox reaction, and it's because we do have a change of the disposition of electrons. Here on the reactant side, they're equally shared between the atoms. Here on the product side, they spend more and more time around one atom than the other. So there is movement, there is transfer of electrons. It's just within the molecule. And so this is called intramolecular electron transfer. So you can have redox reactions either by intermolecular electron transfer, or you can have redox reactions from intramolecular electron transfer. Okay, thank you for listening, and we'll see you next time.